Welcome to module 5 of the course Ultrafast Optics and Spectroscopy. In this module, we'll study transverse electromagnetic mode of ultrafast laser. Often in ultrafast laser spectroscopy lab, we represent propagation of laser beam with a ray. Rays are idealized or oversimplified model of the laser beam. Let's say I have a source and we show that there is with a line we show that laser is propagating along this direction. But in reality, a laser emits a beam of finite width or diameter. If a piece of paper is placed on the laser beam, just like the one here, we get a cross-sectional area illuminated by the laser beam. What we observe is called transverse electromagnetic mode. This is also, in short, this is also called TEM. When transverse electric field intensity of the laser beam can be expressed by a Gaussian function, which means if I take a cross section of what I am observing and plot this cross section as a function of x, this is to be x equals 0, then the intensity profile, we find the maximum of the intensity occurs at the center here, and the wings are less intense. These are less intense regime. Now, if this kind of spatial profile, intensity profile, can be expressed by Gaussian function, the beam is called Gaussian beam. Now, we have to distinguish here, if this beam is Gaussian beam, this is different from the Gaussian envelope which we talked about. Electric field in time domain was expressed by AT e to the power I omega naught t minus k naught z. Sometimes we said that electric field envelope can be expressed as e to the power minus AT square. This is time domain description of the pulse, and we said that field envelope can be expressed or represented by a Gaussian function in time, but this Gaussian function is in space, is a spatial profile. But we have to remember that even if it is represented by a Gaussian beam, Gaussian function, we know that the Gaussian beam spreads from minus infinity to plus infinity. Then how do we define diameter of a Gaussian beam? Should we consider this circle, yellow circle, or should we consider this black circle? In many laser-based experiments, finding out fluence, which is defined as energy per cross-sectional area, fluence is defined by energy per cross-sectional area, and which depends on the size of the laser beam, that is cross-sectional area, becomes very important, and that's why it is important to define the diameter of the beam. We have already seen that a pulse can be decomposed into carrier wave and the field envelope as shown here. So this is your time axis, and this is your field, temporal field, and a pulse has carrier wave that is represented by this complex component, and it has a field envelope as well, which is expressed by this AT. So far, this field envelope is expressed as a function of time. But we have to remember that this field envelope can also be a function of spatial coordinate. This is called spatial field envelope. If we express this envelope function, there should be another t here. So it depends on time as well as space. So the final expression for more appropriate electric field of a pulse is this one, where the envelope function is a function of space as well as time. But to simplify the problem for the present context, we will turn off this time dependence and we'll just check the spatial dependent field envelope. If we take this equation and plug that in, this equation, this is the wave equation in vacuum, then we find this expression. And in order to solve this equation, we have to get the second derivative with respect to space. If we get the second derivatives and with respect to time also second derivative, it's very simple math, one can go over it quickly. Finally, we get this expression. And we know that in vacuum k is related to omega by this expression. So we can plug that in and we get this expression. Now we shall make paraxial approximation, which says that field envelope gradually varies along the z axis. Therefore, we can write down that the second derivative of A is much less than the first derivative of A, and that is why this second derivative term can be considered to be 0. So we reorganize the equation and we finally get an equation which is called paraxial wave equation. The paraxial approximation assumes that all light waves are travelling nearly parallel to the z-axis. Laser beams are coherent and directional, and thus laser beams typically obeys this approximation. We can solve the paraxial wave equation and we can get infinite set of solutions. Each one represents transverse electromagnetic mode. So if we solve this equation, we get TEM, transverse electromagnetic mode, different transverse electromagnetic modes. This TEM is expressed in terms of two Hermite polynomials, and this is expressed by two Hermite polynomials of m and n orders. The lowest order transverse electromagnetic mode we get when m equals 0 and n equals 0, and that is why this lowest order solution is called transverse electromagnetic mode 00, TEM00 mode. This lowest order solution represents a Gaussian beam, which means that if I take a cross section like this way, make it as a center x equals 0, and if I plot the intensity variation as a function of time as a function of x, then I get a Gaussian function. The TEM00 solution of the paraxial wave equation, which features Gaussian beam, can be written as this. So, this is the final solution for the lowest order solution A00. This represents a Gaussian beam, spatial beam, and intensity of this is nothing but square modulus of the solution, the field, and we get this expression for the intensity. A Gaussian beam propagating along z direction is depicted here, featuring some of the important parameters. The first parameter we should note is the beam waist, omega w naught, which is the narrowest size of the beam. Size of the beam is defined as the radius. It is actually expressed in terms of radius. Gaussian beam spot size is represented by this radius. Then we look at another parameter, size of the beam. Size of the beam is changing as we move along the z direction. So, it is expressed in terms of as a function of z with the help of this expression. Here z naught is called Rayleigh length. Rayleigh length is the distance along the propagation direction of the beam from the waist to the place where the area of the cross section is doubled. So, this length is called Rayleigh length, Z naught. So, these are the characteristics of TEM00 mode. Most of the laser system which are built in the Ultrafast lab, they are of TEM00 quality. That is why you should know this characteristics of TEM00 mode. With this, we have come to the end of this talk. In this module, we have discussed TEM00 mode, what is the source of TEM00 mode, how do we get that mode, and what are the characteristic features of that mode. We will meet again in the next module.